Hello everyone and welcome back to a new video in programming the finite element method using MATLAB. In this video we are going to continue our efforts in finalizing something called calculating the equivalent nodal forces, and we are stuck in dealing with the bar forces or bar loads. Those are loads applied in the middle of the bar, and trapezoidal bar loads, which are distributed loads applied on 2 points on the bar. We have programmed the background and the fundamental stuff in the previous videos, but what is remaining is the actual implementation of the calculation itself. And that's what we shall do. Now, before I start, I want to give a reminder that this is part of a video series, which is linked on the top right, about the FEM and about the programming itself. Both are linked on the top right. Take a look there before you dive into this video if you are needing some context. As per usual, I want to remind you that all my dear channel members will have access to the source code fully. But if you are not a channel member, then don't worry, because the entire source code will be written in front of you, meaning that you can write along and you would have the exact same source code as mine. So with that being said, and without further ado, sit back, relax, and enjoy the show. Alright, so we need to start with calculate equivalent nodal, etc. So I'll basically just copy this entire thing here and go and declare me a function that takes those input parameters. So I basically go down, because we have a region. Remember, we made a region. If you go all the way up, let me make those smaller. If you go all the way up, you know that we have made a big region that says equivalent nodal load calculations. And that's why we have a region, because there's so many things we need to program. Now, here in the ENL, for the concentrated loads, let's start with the concentrated loads. I'm going to basically take this function declaration and declare it myself to be able to deal with it. Let me collapse this distributed load and call here a function and basically provide it with Q1 and Q2. Those are the output parameters we're asking when we have the axial stuff here. And we're going to say this equals the function call. Now I need to change some things. I'll keep L1 as it is. For the local input, this means the load force. So I'll say here force or load and fem bar. And here, this is actually not really hard. You see, I actually did derive some of this stuff. For example, I have a derivation from mechanics of materials, or a derivation based on the work equivalence method. The way you calculate equivalent nodal forces depends on the virtual work method. And that's basically the two forces. Those are like part of the derivations. I actually banked on Gemini a little bit to this AI thing, but I also double checked with my own derivation of mechanics of materials, and that's the case. Now, basically, those are the equations you should know using virtual work method, but I'll just take the functions as they are. So for the axial load, because the strain is constant, meaning that displacement is linear, so there's a linear relationship between the right side and the left side. Q1 is, of course, the output of the right side, and Q2 is the output of the left side. So here, Q1 is going to be declared to be the force, or the load in this case. Maybe I should call it axial load, because it's specific. So it's the axial load multiplied by the length of the fem bar minus x, which is called L1 here, divided over length. So divided over the fem bar dot length. And Q2, you can say it's axial load minus Q1. That's perfectly fine. Or you can just declare that it's basically axial load multiplied by the x divided by fem bar dot L. Fantastic. Those are the outputs for the equivalent nodal from the axial. So we have solved one issue. Now we need to continue and copy this stuff and declare a function with that name. So I'll go down again here and I'll paste this. So I'll declare a function. This time I have a lot of Q's, so Q1 and Q2. I think I should just copy the entire sentence here. I think I blundered something. I forgot to pass in the object, right? Did I pass in the object? No. I should always pass in the object because of object-oriented programming in MATLAB. It's kind of weird, but it is how it is. Since I don't need it, I can just tilt it out. So let's paste this entire thing and apply a tilt for the object. Now here I'm giving L1. I should call this shear force and fem bar. Now here, to know exactly what the equivalent force is, I can go to Daryl Logan's book, because it includes something about that stuff. So give me a sec, let me just open it. Okay, so in Daryl and Logan's book, of course I cannot show you the entire book because of copyright issues, but I can give you an outtake of it. In Daryl and Logan's book, in appendix number D, you can see the equivalent nodal forces in its glory. So I basically implement it, and you can see, yeah, there we go, the single shear force. The single shear force will cause a force in the beginning, a force in the end, a moment in the beginning, and a moment in the end. And if I remember correctly, let me check very quickly how I did this. Okay, what are my outputs? It's shear, moment, it seems, right? Yeah, it's shear, moment, shear, moment. So I need to give back shear, moment, shear, moment. Let's do some commentary here. Q1 is shear at node 1. Q2, let me just double check for good measure. Q2 is added to the moment, yes. So Q2 is moment at node 1, and Q3 is shear at node 2, and Q4 is moment at node 2. So it's P B square L plus 2A. Let me just write the values here. So P is actually the shear force in those equations. I like to rewrite it like this. B is L minus X. A is L1 in this case. And B is fem bar dot length minus L1, which is basically the remainder. You know what? Let's get L for good measure. So let's put L here, which equals fem bar dot length. Okay, now we can basically calculate those from the equations. So now this is basically the calculate equivalent nodal forces. I don't know why the error didn't subside, basically. It should subside. That's quite a strange thing to think about it. Let me just check why. Oh, it's because there is object dot. Yeah, I should have known that. Now it should be subsiding. Let me see. The error went away. That's true. Now I need to copy this entire thing again and do it for the moment. Okay. What's this? Torsion? Okay, the torsion. Now the torsion is easy. It's going to be very similar to the axial force. The reason why it's very similar, because the entire derivation is actually really similar. Look, you're going to say basically delta. You're going to basically say that torsion 1 multiplied by the length of 1 divided by jg is going to equal to torsion 2 multiplied by length 2 divided by jg. So in the end, torsion 1 multiplied by L1, it's going to be a copy-paste scenario here. Torsion 1 L1 equals torsion 2 L2. So you can see that we're starting exactly here, which means we're going to end exactly here. So I can basically just copy-paste my axial for the torsion, I guess, because it has a similar derivation. So what I will do is I will copy this definition and I will paste it. I'll generate a function, paste this entire function call. It's called function signature, by the way. And now here, let's change it. This now, of course, is a torsion moment, so I'll give here a torsion. And all I have to do, now I think it's called Q3 and Q4. Is it called Q3 and Q4? No, it's Q1 and Q2. Okay, fine. So all I have to do is to copy paste this stuff, because the relationships are going to be the same, despite the fact that it's a torsion moment. Now here, it's not called axial load, it's called torsion moment here, and it's called torsion moment here. Well, I think the torsion equivalent moment has been calculated, and that's that. Now we go for the final stretch, which is the last of them. For the, of course, bar force, there is still the distributed load, which is a lot of headache. But at least for the bar force, the last one is the equivalent for the moment. Let me check very quickly what those mean. So Q1 is once again shear 1, that's moment 1, shear 2, moment 2. Yeah, that's the case. So I'll basically control paste here. I'll declare a function, of course, and end my function declaration. The object has nothing to do here. And what I will do is I will copy part of those definitions, because those help me in the long run. Here I will call moment instead of, or bending moment. And now I'm going to go to the book of Daryl and Logan and see what happens here. So, in the book of Daryl and Logan, surprisingly, he assumes the clockwise to be positive, despite the fact that counterclockwise in 2D should be positive. So once again, it seems that I have to apply a negative value for all those things. I have no idea if it works or not. You know what? If it doesn't work, then I will go to my good old integration approach. But for now, let me take Daniel and Logan's approach for a spin and see what happens, basically. So here, once again, I need A. A is, of course, L1. L is fem bar dot length. And B is L minus A. And M is the bending moment. With, of course, keeping in mind that the signs are inverted now. So Q1 in this case equals M. I'm taking it from Daniel Logan's book, but without the semi-negative. I multiplied the entire equations by -1. Fantastic. So this should be the equivalent forces of a moment. And this should be the end of the calculation equivalent nodes for bar loads concentrated. Now we still have the entire doom that is called bar load distributed, but I think that this is a win I will take, and I will think about the other functions about the distributed loads in the next video. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give an equivalent load size shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on. Especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and I will catch you in the next video. Bye bye.